right, so metamorphic rocks form anywhere where there's intense heat and or pressure, but where does this happen? What are metamorphic environments? There's a lot of different environments where this can happen. We are going to focus on just a few, but just to list them out, right? Contact metamorphism, dynamic metamorphism, regional metamorphism. Those are the ones we're really going to talk about, but they could also happen due to deep burial, hydrothermal, meaning there's hot water circulating through the lithosphere. It could happen because of subduction or even because of shock, right? So when a meteorite impact or a lightning strike, that can produce metamorphic rocks. But we're going to focus on just a few of these. Contact metamorphism or thermal metamorphism. This is due to the heat when a rock is in contact with a body of magma, right? That body of magma is so hot that the heat radiates into the rock around the magma chamber, metamorphizing the rock around it due to contact metamorphism, right? So the rocks that are close to the magma chamber, those are going to be the most metamorphosed. The rocks that are further and further away from the magma chamber, those are going to be the least metamorphosed. Dynamic metamorphism. This is metamorphism that occurs because of parts of the earth moving, right? Dynamic just means movement. Right? So any places where there's high level of differential stress, like in a fault zone, a plate boundary, you can get dynamic metamorphism. And this is one of my favorite types of metamorphism because it produces really pretty structures in a rock. So anytime where you have movement, you can get shear, right? Where parts of a rock are moving at different directions than other parts of the rock. And you can create grains that start to roll around, creating a structure that we call myelinite. Garnets also are often created in these environments. We call those rotational garnets. So you get a rock, and when you look at the foliation in that rock, it almost looks like storms or waves. It's very pretty flowy, spirally, and that's because of dynamic metamorphism, right? The movement, the shear stress. You can also get regional metamorphism, right? So this is when the metamorphism isn't restricted to just one location, right? It's not just around one magma chamber. Instead, it's a whole region that is undergoing intense heat and or pressure, right? This could be like at a subduction zone, right? Where along an entire plate boundary, you get intense pressure, intense heat happening where these plates are colliding. And then you're going to get a lot of metamorphic rocks forming around the entire region. Right, some at high pressure, some at low pressure, some at high temperature, some at low temperature. There's going to be a range of metamorphic rocks created. All right, so as we've talked about, right, there are different grades to metamorphism. Right, you start with the parent rock, you start with the protolith, you add a little bit of heat and pressure, and you get low grade metamorphic rock. You add a little more heat and pressure, you get medium grade. You add a little bit more heat and pressure, you get high grade metamorphism. So there's this gradient of grades up until you get to melting, right? And remember, if it melts, it's then igneous. If it doesn't melt, if it stays a solid, then it's metamorphic. So low grade, slight metamorphism, high grade, intense metamorphism. And different minerals form at different grades, right? Different metamorphic minerals form at different grades. So for example, the mineral chlorite forms at a low grade, but the mineral garnet forms at a medium to high grade. Right? So if you see garnet in a metamorphic rock, you know that it has to be a medium to high grade metamorphic rock. If you see chlorite in a metamorphic rock, you know that it has to be a low grade metamorphic rock. Right? So this means that metamorphic rocks have index minerals, right? There are some minerals that only form in low grade, some minerals that only form in high grade. Right? So if you see a group of minerals in a metamorphic rock, you can figure out the grade of that metamorphic rock. And we call those minerals that exist together the mineral assemblage. Right, so for example, looking at this figure, you can see it's possible to have just the right temperature and pressure combination for sillimanite, kyanite, and garnet and biotite to all form together, right? They overlap at the same temperature pressure area. However, you're never going to see these minerals, or you're very, very rarely going to see these minerals with chlorite because they just don't form at the same temperatures and pressures, right? So a mineral assemblage is all of those minerals that can form in the same type of temperature and pressure. And this allows us to use these index minerals, these mineral assemblages, to create maps of metamorphism. Okay, so this is a map of the Northeast US, and you can see that with the colors, we can look at minerals and these index minerals and these mineral assemblages to figure out where was the most intense metamorphism. Oh, it looks like it was in Massachusetts. And then as we get farther and farther out of Massachusetts, right, we see that the metamorphism decreased because the minerals there tell us that metamorphism was low there, low grade. All right, metamorphic facies, that's just a set of mineral assemblages, right? A group of minerals that all form together that indicate a range of pressure and temperature conditions. So for example, if we see a lot of hornfels, we know it's probably contact metamorphism. If we see a lot of eclogite, we know it's probably metamorphism due to deep burial. Okay, so these metamorphic facies let us understand what type of metamorphism we see and what type of environment that metamorphism had to have taken place in, right? Were those rocks formed by subduction zones? Were they formed by contact metamorphism near a magma chamber? Were they formed due to intense pressure because of mountain building, and so on and so on, right? So this is one way that we can use rocks to figure out the past of that environment. What pressure and temperature conditions had to be present in order for these rocks and these minerals to exist, using rocks to interpret the history of Earth. All right, that's all for now. Next up, we're looking at sedimentary rocks.